Hello friends, I am here again with a new concept of lens, that is cutting of lens and combination of various parts of a lens. So in this video we will learn following topic, cutting of lens, and under the section of cutting of lens we will learn that if a lens is cut along principal axis, then what is its effect on focal length, intensity and other factors including power, etc. And if the same lens is cut along optical axis, then what will be the effect on focal length, intensity, power and others. And when the various parts of lens are combined, then what will the effect on focal length, intensity and other factors, and the combination of these various part of lens are done in the same orientation or in opposite orientation. So we will learn all these concepts in this video, and in the last we will learn on the cutting and combination of lenses. So stay tuned, please subscribe it, like it, share it and press the bell icon. Thank you and happy learning. So we will learn the cutting of lens. So clearly a lens can be cut by various ways. That is, it can be cut along the principal axis, along a line parallel to principal axis. It can be cut along principal axis. It can be cut along optical axis on or any other way. So we will basically consider two cases when the lens is cut along a principal axis or a lens is cut along optical axis. So here first, when the lens is cut along principal axis, so if you cut a symmetric lens along a principal axis, then it will give you a two equal parts, which is shown here, and we will calculate the focal length of individual part, and we will find a relationship between new small lenses or new cut lens with the original lens. So this is our lens L1. This is our original lens, and if we cut this lens along symmetric along a principal axis, and if we cut this symmetric lens along principal axis, then it will form two lenses L1 and L2 and L3. So what will be the focal length of L2 and L3? If the focal length of original lens is f and its power is p, then the focal length of new lens will also be f, and we know that the power is inversely proportional to focal length, so clearly power will also equal to p. So how this focal length is same as the original focal length? So we will calculate it. First we will calculate the focal length of original lens, that is for lens L1. So for lens L1, if the mu be the refractive index of this material, then focal length 1 by f is equal to mu minus 1 by r1 minus 1 by r2. So this is our equation 1. If you see here lens L2, for lens L2, the focal length, if it is considered as f1 or f2, then 1 by f2 is equal to mu minus 1. The radius of curvature of the first surface is r1, the radius of curvature of second surface is r2. So again 1 by r1 minus 1 by r2. Now you just solve it first. So for the original lens, r1 comes with a positive sign and r2 comes with negative sign. So 1 by f1 is equal to mu minus 1 by r1 plus 1 by r2. While for the lens L2, r1 comes with positive sign and r2 comes with negative sign. So we get mu minus 1 by r1 plus 1 by r2. Similarly, if you calculate for lens L3, then and its focal length, if it is f3, then 1 by f3 is equal to mu minus 1 by r1 plus 1 by r2. So if you compare this equation 1, 2 and 3, then clearly f is equal to f2 is equal to f3. That is the focal length of this cut lens and the original lens are same. So as we know that power is inversely proportional to focal length, so power will be also same. So all these concepts are written here as none of refractive index mu r1 and r2 will change. The focal length of each part will be equal to that of the initial lens. So again, what will be the intensity? So if you see here, we just define intensity in terms of aperture of lens. So aperture is the effective diameter through which light ray transmits. Aperture is the diameter of effective light transmitting area. So if you see here, the aperture of this original lens is, if this is d, then it is reduced here. So clearly when we cut a symmetric lens along the principal axis, then the aperture will be reduced. Accordingly, the intensity of image formed will be reduced. So clearly, when we cut a lens symmetrically along the principal axis into two equal parts, then the focal length will remain same, power will remain same. However, the aperture reduces, and because of that, the intensity of image reduces. Now, if cutting is done along any line parallel to principal axis, so instead of symmetrical cut, if we make asymmetrical cut, but the cutting is done along any line parallel to principal axis. So in that case, we will see that we get two lenses. The radii of curvature of both surfaces are R1 and R2 respectively, as was in the previous case. So clearly the focal length depends only on the refractive index and the radius of curvature, and because of that we get the focal length remains same, the power will remain same. However, the aperture reduces. So, so as the aperture reduces, the intensity of image formed by a lens reduces. So if you see here that if I cut this lens along this line I1, then we get this figure, and in this case the focal length again will be f and p. However, the intensity of image formed by each lens will be as per the size of their aperture. And if I cut the lens along this line L2, then we get basically two lenses, two small lenses. One is this and other one is big one. So clearly the focal length and power of both lenses are same, as the radius of curvature are same for both surfaces. Cutting along line parallel to principal axis will not change focal length or power, as power is inversely proportional to focal length. It only changes the intensity of image, as aperture of each lens reduces, so intensity as being directly proportional to a square of aperture, intensity also reduces. And this is true of any kind of lens, whether it's convex lens or concave lens. So if we take this lens, suppose this is our lens, this is our concavo convex lens, and if we cut this lens along this line, then again the intensity, then we get two lenses basically, and the focal length and power of both lenses will be same. Both lenses will form the complete image. All parts of lens will make complete image. There is no any change in focal length or power of the lens. Only the intensity of image will be reduced. Now consider the case here. The refractive index of lens material is mu, and the first surface having the radius of curvature equal to R1, the second surface has radius of curvature equal to R2, and considering R1 is equal to R2. So we will calculate the focal length when the lens is cut along the optical axis along two parts, and see that what is its effect on the focal length. So for the original lens, 1 by f is equal to mu minus 1 into 1 by r minus 1 by r2, where r1 and r2 are the radius of curvature of first and second surface. Again, we consider the direction of incident light ray as positive. So R1 comes with positive sign, R2 comes with negative sign, and here mu minus 1, 1 by R1 plus 1 by R2. So R1 and R2 is equal to R, so we get mu minus 1 into 2 by R. So from there we get F is equal to, or the focal length of original lens is equal to R divided by 2 mu minus 1. So this is our equation 1. Now we consider the second case when we cut this lens along the optical axis, and in turn we get two plano-convex lens. So these are two plano-convex lens. We call it L2 and L3 respectively. So for L2, for lens L2, focal length is suppose f1, then 1 by f1 is equal to mu minus 1, 1 by r1 minus 1 by r2. R1 is equal to R, and it will come with a positive sign as this direction is positive, and again here r is equal to infinity. The radius of curvature of second surface will be infinity. So from there we get it's mu minus 1 by r minus 1 by infinity, and we get mu minus 1 by r. So f1 is equal to r by mu minus 1. Now for this lens L3, 1 by f2 is equal to mu minus 1 by r1 minus 1 by r2. Now if you see r1 and r2, then r1 is equal to infinity. The radius of curvature of first surface is infinity, while the radius of curvature of second surface is minus r. So from there we get mu minus 1 by infinity minus 1 by minus r, that is equal to mu minus 1 divided by r. So f2 is equal to r divided by mu minus 1. So if you compare f1, f2 and f, then clearly f1 is equal to f2 is equal to f into 2. That is the focal length of cut lens L2 and L3 become twice the focal length of original lens. So as we know that the focal length f is inversely proportional to power. So power of this cut lens, we call it P2. So P2 is equal to P by 2. As its focal length become twice, so power will become half. Clear, it's very clear that when the focal length become n times, then power will reduce by n times. So P2 is equal to P by 2 and P3 is also P by 2. Cutting a lens along optical axis in two equal parts will make the focal length twice and power half. So all things are written here, that it is true for equiconvex as well as the equiconcave lens. So for equiconvex or equiconcave lens, the focal length of each part will double, the power of each part will become half. And in this case we also see that the aperture will same, that is the light transmitting area of each lens will be same as the original lens, and because of that we get the image is of equal intensity. That is, there is absolutely no any reduction in the intensity of image if we consider the image through this original lens and if we consider the image through each cut lens. So in this case we just see that the power or focal length changes, however the intensity of image will be same, the aperture will remain same. When convex or concave lenses have different radii of curvature. So for lens L, the radius of curvature of first surface is R1, while the radius of curvature of second surface is R2. The refractive index of material is mu, and the focal length is f, and power of lens is p. So again we just calculate by using lens maker formula. 1 by f is equal to mu minus 1 by r1 minus 1 by r2, that is equal to mu minus 1 by r1 plus 1 by r2. This direction will be taken as positive. So from there we get f is equal to, or in fact we just write in this way, that as r1 is not equal to r2, so we will write in this way: 1 by f is equal to mu minus 1 into r1 plus r2 divided by r1 into r2, and we get f is equal to r1 r2 divided by r1 plus r2 into mu minus 1. So this is the focal length of original lens. We call it equation number 1. Now if we cut the lens into the optical axis, making it into two parts, then the focal length of first part is f1. So 1 by f1 is equal to mu minus 1 by r1 minus 1 by r2. Here r1 comes with positive sign while r2 is infinity, so we get mu minus 1 by r1 minus 1 by infinity. It is, we get mu minus 1 divided by r1, and f1 is equal to r1 into mu minus 1. Similarly, if we calculate f2, then 1 by f2 is equal to mu minus 1 by infinity minus r2, and we get f2 is equal to r2 divided by mu minus 1. So if we see equation 1, 2 and 3, then clearly f1 is not equal to 2f, or f2 is not equal to 2f, which we saw earlier, that when the radii of curvature of both surfaces are same, then we get f1 is equal to 2f and f2 is also equal to 2f. However, here f1 and f2 is not equal to 2f. Now in order to calculate the power, what we do, power is inversely proportional to 1 by f. So P1 is equal to 1 by F1, and it is mu minus 1 divided by R1, and similarly P2 is equal to mu minus 1 divided by R2. So clearly this is the case when the convex lens have different radii of curvature. Now we will see a case of concave lens. Consider this biconcave lens. Here the radii of curvature are R1 and R2 respectively. The focal point of the focal length of this biconcave lens is f and power is p, then and the refractive index of material is mu. Then clearly again we just apply the formula, then we get 1 by f is equal to, if you apply the lens maker's formula, then we get the value of focal length. So 1 by r1 minus 1 by r2. Here r1 comes with negative sign and r2 comes with positive sign, so we get minus mu minus 1 by r1 plus 1 by r2. And similarly, if you consider this lens L2, so for lens L2 we have mu minus 1 by r1. r1 comes with a negative sign, so minus r1, and r2 comes with a value equal to infinity, that is 1 by infinity. We get minus mu minus 1 divided by r1. So this is the value of 1 by f1. So from there we get f1 is equal to r1 divided by mu minus 1 along with negative sign, and similarly we get f2 is equal to minus r2 divided by mu minus 1. So clearly in this way we can calculate the power as the inversely proportional of focal length, and we can see that in case of biconcave lens also, if we cut the lens along the optical axis and if r1 is equal to r2, then for this cut lens f1 is equal to twice f and f2 is also equal to twice f. So clearly the focal length become twice or power become half if we cut a biconcave lens into two equal parts. Now we will learn combination of parts of a lens. So if lens has been cut along the optical axis and then joined. So consider this figure. Here we have one lens having refractive index mu. The focal length of lens is f and the radii of curvature of both surfaces are same and it is equal to r. So then if we cut this lens along the optical axis, then we get basically two equal parts. Based on the orientation of those two equal parts, we get these four possible combinations. So this is the first combination, when the convex surface of one lens is attached to the plane surface of second lens. So here if you see this figure, then as we know that the orientation of any lens does not change its focal length. So if I place this lens along this way or along in other way, the focal length will remain the same. That is, if I place a lens along this way or if I place a lens along this way, the focal length will remain same. So if the focal length of individual lens, so the focal length of individual lenses are 2f, as we have already learned. So the focal length of combination, so we calculate the focal length of combination by using 1 by f equivalent is equal to 1 by f1 plus 1 by f2, as these lenses are placed in contact of each other. So clearly f1 and f2 both are equal to 2f. So 1 by f equivalent is equal to 1 by 2f plus 1 by 2f. That is equal to 2 by 2f and is equal to 1 by f. So focal length of equivalent lens is equal to f if we combine the cut length in this orientation. Now if we combine the cut length along the orientation as shown in figure B, focal length of individual part is 2f. So 1 by f equivalent is equal to 1 by 2f plus 1 by 2f, that is 2 by 2f, and from there we get the equivalent focal length is equal to f. Now if we make the orientation as per this figure C, then again we will see that 1 by f equivalent is equal to 1 by f and f equivalent is equal to f, and as per the orientation D, again f equivalent is equal to f. So as we know that the power is inversely proportional to focal length, so power here is also equal to P. In this case also we have power equal to P, in this case power P, and in this case power P. So clearly if we cut a lens along the optical axis and join in any orientation, then the focal length remains same, the power remains same, and also the aperture of lens remains same, then clearly the intensity of image formed will be same. Now if lens is cut along principal axis and then joined, so if lens is cut along principal axis and joined in two ways, then so this is the first way of joining, so we call it A, and this we call it B. So if the orientation of cut lens are same, that is if cut lens placed with erect orientation, then it will behave as a convex lens having a positive focal length, and it focuses the light ray in downward direction. So consider this is the light ray, then this first lens L having focal length f will converge this light ray in downward direction. Now the second lens L, we call it L2. So now the second lens L2 converges the light ray again, and the final image is formed in this way. So clearly if you see here, the light ray is converged by both lenses, and in this way both lenses behave as a convex lens having positive focal length. So the focal length of combination will be 1 by f equivalent is equal to 1 by f1 plus 1 by f2, and focal length will be same, so 1 by f plus 1 by f, that is 2 by f. So f equivalent is equal to f by 2, and power equivalent is equal to 1 by f equivalent, that is 2 by f, that is 2p. So if you see here, the power has been increased twice than the power of original lens. So if we cut lens is placed with erect orientation, then both lens will converge the light ray. Both lens have positive focal length, and both lens focus the light ray in downward direction. Because of that, the focal length of combined lens will be half of the focal length of original lens, and power of combined lens will twice the power of original lens. Now if both lenses are placed in different orientations, that is one lens is placed in inverted orientation and other is placed in the erect orientation. So if we see here that this first lens is placed in the erect orientation and the second lens L2 placed as inverted orientation, if you see the light ray, then when the light ray comes, then first lens L1 will converge this light ray. However, the second lens L will diverge the light ray, and because of that the light ray moves undeviated. So the second lens L2 focus the light ray in upward direction, and it will have a negative focal length. So as we know that the focal length of each part will be f, so the focal length of first part will be f and the focal length of second part will be minus f. So 1 by f equivalent is equal to 1 by f1 plus 1 by f2, and it is equal to 1 by f minus 1 by f, that is equal to 0. So power is equal to 0 and f equivalent is equal to infinity. So the combined lens will behave as a lens equal to 0 power or infinite focal length. So an equiconvex lens is cut into two halves along x axis and y dash as shown in figure. Let f dash and f double dash be the focal lengths of complete lens of each half of case A and each half of case B respectively. Then you have to find the correct statement out of these following four. So if we cut the lens along the x dash, then it means we are cutting the lens along the principal axis, and in this way the focal length remains same. So clearly f dash must be equal to f. And again, if we cut the lens along the y dash, then it means we are cutting the lens along the optical axis, and in this case f double dash will be equal to 2f. So if you see the option, then option C is correct. F dash is equal to f and f double dash is equal to 2f. Now this is the second problem. A thin symmetrical double convex lens of power P is cut into four parts as shown in figure. Power of A is 2P, P by 2, 3P or P. So as we already know that if we cut a lens along any line parallel to principal axis, then its focal length remains same, and as the focal length remains same, then power also remains same, only the intensity of image formed by that cut lens decreases. So clearly power of lens part A, B, C, D in all will be equal to P. So power of all part will be equal to P. Again, all part will form the complete image of the object. And this is the third problem. This is in fact very good problem. The problem says a symmetrical converging convex lens of focal length 10 cm and diverging concave symmetrical lens of focal length minus 20 cm are cut from the middle and perpendicularly and symmetrically to their principal axis. The parts thus obtained are arranged as shown in figure. The focal length of this arrangement is, so as per this problem, this is our symmetrical convex lens, and if we cut this lens, the focal length of this lens is 10 centimeters. So if we cut this length, then we get two parts of this lens, and the focal length of each part will be 20 centimeter. Now it is also given that a symmetrical diverging lens and the focal length of this symmetrical diverging lens is minus 20 centimeter. So if we cut this symmetrically diverging lens along the optical axis, then we get basically two symmetrical diverging lens, and the focal length of each part will be equal to minus 40 centimeter. Now the problem says that we just place these combinations into the way it is shown here. That is, if this is the lens L1, this is the lens L2, this is the lens L3, then we combine L1 and L2 and form one unit, and then place a lens L3 at a distance 20 centimeter. So you have to calculate the focal length of this arrangement. So the focal length of this part, this L1 plus and L2 combination, will be 1 by F equivalent is equal to 1 by F1 plus 1 by F2. And as we know that the orientation or the change of orientation of any lens does not impact its focal length. So anyway, F1 is equal to 20 centimeter and F2 is minus 40 centimeter. So 1 by 20 minus 1 by 40, and from there we get 2 minus 1, that is 1 by 40 centimeter. So F equivalent is equal to 40 centimeter. So focal length of this unit 1, we call it unit 1, is 40 centimeter. Now if we see this unit 2, so for this unit the focal length is minus 40 centimeter. So we call it F1, we call it F2. Now we have to calculate the focal length of this combination. So as we know that if two lenses are placed by a distance equal to some D, then the focal length of combination is equal to 1 by F equivalent is equal to 1 by F1 plus 1 by F2 minus D F1 F2, and you have to also consider the sign. So 1 by F equivalent is equal to 1 by F1, so 1 by 40, and F2 is minus 40, so 1 by minus 40 minus D is equal to 20 centimeter, and F1 is 40 and F2 is minus 40. So if you solve it, then you get the answer equal to 20 divided by 40 into 40, that is 1 by 80, and F equivalent is equal to 80 centimeters. So clearly, as the equivalent focal length comes with positive sign, so it will work as a converging lens. So the system will work as a converging lens. Again, if you see here, like as we know that the inverse of focal length is power. So if we convert this equation into power in terms of power, then P equivalent is equal to P1 plus P2 minus D P1 P2, and power is in diopter. So as power is in diopter, so clearly diopter power is equal to 1 by F in meter or 100 by F in centimeter. So in that scenario, if we have to calculate the power, then we should take D in terms of meter. However, here we have to calculate the equivalent focal length, and all focal lengths are given in terms of centimeter. That's why we have taken D in terms of centimeter also. So it's very important that you should take here D in centimeter, while if you calculate the equivalent power, then you have to take D in meter. So suppose that the power of one system is plus 5, power of second is minus 10, and D is given as 20 centimeter, then P equivalent will be 5 minus 10 minus 0.2 into 5 into minus 10. So this is the important concept I wanted to share with you. So this is the important concept which I wanted to share with you.